Hi, we're going to finish up the last topic in Focus 3. So we're still talking about entropy and trying to understand better the Gibbs free energy, which is how chemists decide if a process is spontaneous or at equilibrium. So we'll introduce the Gibbs free energy in this topic, and then we'll have a whole chapter on how you use a Gibbs free energy change in physical processes, things like phase transitions, and then we'll have a whole nother chapter after that on chemical reactions and the Gibbs free energy change. So let's. Okay, so this is topic 3D, the Gibbs energy. So it's a new thermodynamic function. You've used it in other courses and you saw briefly where it came from in Chem 108, but this will be a little bit more detail. So the key idea in this topic is that if the temperature and pressure are held constant during a process, then the direction of spontaneous change is towards lower Gibbs energy. So we're going to totally understand that when we finish up this topic. So we know lots of cases where a reaction might produce gases or use up gases, where we would be able to determine the direction of the reaction if it was just the system's entropy that mattered. But we need to be able to determine the entropy change of the whole universe when a process takes place. So you might say, well, in photosynthesis, the entropy decreases because you're taking gases out of the atmosphere, making sugars, so you're making fewer molecules. But that's not necessarily the case. Sometimes that's true. You decrease the number of gas molecules and a process isn't spontaneous, but we need to understand in the process of photosynthesis what happens to the surroundings and what happens to the reaction's entropy in order to make that decision. So we're going to make that into a totally quantitative process, which is something you'll get very used to in PChem, because it's really about trying to take things that are natural tendencies or natural processes and put them into mathematical equations. So the first thing, we haven't done this yet, is calculate the entropy change for a reaction. So you can look in the back of your book. There's a table just like there was in the Gen Chem book that gives you the absolute entropies. So remember, entropies aren't changes in entropy in the back of your book. They're absolute because we're saying this is the entropy compared to absolute zero for a substance. So you can look up the molar entropies and multiply. Nu is the stoichiometric coefficient, so products minus reactants. And you can get the delta S for the standard conditions of any reaction. And let's just do self-test 3D.1. So we want to calculate the standard reaction entropy for the formation of 2 moles of NH3 gas from the elements in their stable states. So what's the change in entropy when 2 moles, well, just for A, we're just going to calculate the standard reaction entropy for that reaction. So here's our reaction, and it's a formation reaction, but remember when you're talking about entropy, these don't have entropies of 0 because these are absolute entropies. They're not entropies of formation. So we look up the entropy absolute for nitrogen gas, hydrogen gas, ammonia. Then we're going to multiply by the stoichiometric coefficient. So we'll take products minus reactants and multiply them. So it's 2 times the entropy of ammonia gas, 1 time nitrogen, and now it's subtracted because it's a reactant, and subtract 3 moles of hydrogen. And we end up with negative 198.76. And notice that we have only 2 digits to the right of the decimal in these two. So even though we had 3 here, we're going to be limited in our sig figs by 2 to the right of the decimal. The units are joules per K. When you look up in the back of the book, these will each be molar, but we multiplied then by how many moles we have. So this number is the delta S for the reaction in units of joules per Kelvin. If we only used 2 moles of hydrogen, then we'd have 2/3 of this reaction taking place. So you could go back and balance this and plug those back in here, but you could also just notice that that's 2/3 of this. And so B, which asks for, if you're only using 2 moles of hydrogen, what would the delta S be? It would be negative 132.51. So that's hopefully familiar to you from Gen Chem. And now we want to talk about spontaneity a bit more and then introduce the Gibbs reaction and energy. So the change in Gibbs free energy for a reaction or for a process in general. So the spontaneity of chemical reactions. So the important thing, I've already mentioned this, is that it's essential to consider the entropy of both the system and the surroundings when deciding whether a process is spontaneous. So notice this reaction that they give you is the reaction of hydrogen gas with oxygen gas making liquid water. Well, clearly the entropy change of that is going to be negative. You're going from 3 moles of gas to 2 moles of liquid. And so the entropy actually decreases by 327 joules per K. So if you were only looking at the entropy change of the reaction itself, you would predict that not to be spontaneous. But this reaction is extremely exothermic. And so that means the water bonds are more stable than the hydrogen and oxygen. And so if we considered what happens to the surroundings, you give off tons of heat, that increases the entropy of the surroundings. So we have to take that into account too. So once again, they say exactly the same thing in italics, just in a different way. Whenever considering the implications of entropy, always consider the total entropy of the system and its surroundings. So remember from when we introduced the definition of entropy, the surroundings entropy is going to change by the heat that's given off by the reaction divided by the temperature. So process is carried out at constant temperature. If the reaction gives off heat, then the surroundings absorbs heat, so we'll change that sign. And it's delta H instead of delta U when it's at constant pressure. So that's the important part. We'll make sure we take that into account, because truly this would be the delta S for the surrounding would be negative Q for the reaction over T, and Q is only equal to delta H if it's constant pressure. So that's why we can put delta H in there. So when you look at this, this just has you calculate the total entropy change for the system and surroundings. So for the surroundings in that reaction we looked at above, hydrogen plus oxygen goes to liquid water. If the delta H is negative 572 kilojoules per mole, then we're going to change the sign of that. The reaction gives off that much heat, so the surroundings absorbs that much heat. And we're going to convert that into joules because our delta S for the system is in joules. So delta H, change the sign. So negative 572, change the sign. Whoops. So now it's positive. And so in this process, the surroundings entropy changes by 1.92 times 10 to the third joules per K mole. And when you say mole, in this instance, you're really talking about per how it's balanced. So it would be per mole of oxygen, 2 moles of hydrogen, and 2 moles of water. So the total entropy change would be the number they gave us above, which was the system's entropy changed by negative 327 joules per K mole, the surroundings by a positive, and overall the universe's entropy increases when hydrogen and oxygen react. So it's a very, very, very spontaneous reaction. Let's see if I did that one. No, I didn't. So you stop and do this, which is very, very similar to this one. You're just calculating the entropy change of the system and the surroundings separately and determining the total entropy change of the universe. Not so convenient, really. It's would be nice if we had a function that would allow us to just look at what happened to the system and to decide if the process was spontaneous. So what we're going to do is we're going to introduce a function that allows us to look at just the system. So what you notice is the delta S total, wherever you use that equation, is going to be the delta S of the system minus delta H over T. So if the process is carried out at constant temperature and pressure, this negative delta H over T, which it says right over here, is going to be equal to the change in entropy of the surroundings. So here we've gone from thinking about system and surroundings to everything in terms of the system. So now let's define a new function to make it easy to look at this. So if we define the Gibbs free energy, yeah, I'll do it bigger here. So we define a new function. And it's going to be useful at constant temperature and pressure. So the Gibbs energy is defined. So you can't derive this. We define it out of convenience. So at constant temperature, let's look at what a delta G would be. So if you look at a change in Gibbs free energy, it'll be equal to a change in enthalpy minus, let's write that out. So a delta will be equal to how this changes and then how the product of these two change. So remember, if all of these are state functions, number one, we've defined Gibbs free energy to be a function of state functions, so it's also a state function. Then it's also true if you have a change in the product of TS, if it's a state function, it doesn't matter how you change those. You could change T first and holding entropy constant, and then change entropy holding temperature constant, or vice versa. So you can expand this to be T delta S minus S delta T. So each of these has a negative on it. And then if the process takes place at constant temperature, this term is 0. And this is going to be an important thing to remember. We're deriving what we know about delta G only if the process is at constant temperature and pressure. So, if you look up here, I didn't go through this in detail, but this was the equation we looked at. The total entropy change of the universe is what happens to the system plus what happens to the surroundings. So if you multiply through by T, then you get T delta S total equals T delta S minus delta H. And so if we look at this equation and compare it to this one, you'll immediately see that negative T delta S total, so if you change the sign on this guy, it will be equal to delta G. So let's just do that. So if we change the sign on this guy, and then just change these around so it's this, now the sign is changed to positive, and this will be negative. So negative T delta S total is equal to this. And right up here, we just showed that it's also equal to delta H minus T delta S is equal to delta G. So these are equal to each other. Need to go back up here and make sure we remember this right here. This was only true at constant pressure. And the reason for that is that at constant pressure, here we go. Yeah, so at constant pressure, remember that's the only time that Q equals delta H. So this is technically Q, but if we're at constant pressure, then Q at constant pressure equals delta H. So this right here is true at constant T and P. So we now can look at this, and from the second law, we know that if the entropy changes in a positive way for the universe, the process is spontaneous. So that means that delta G has to be negative. They're always going to have the opposite sign. So if delta G is negative, the process is spontaneous. So we can go back and look at that reaction of water being formed, and we can say, is this process spontaneous? I guess I didn't work it out, but you can just look up the delta G's at standard states and take products minus reactants and determine if that process is spontaneous. So you don't have to go through using the delta H and the delta S. You can just use delta G's. Then it's spontaneous. So okay, so we went through that. So that's one use for Gibbs free energy. So if Gibbs free energy is negative, that means the delta S of the universe is positive and the process will be spontaneous. Only true if it's at constant temperature and pressure. Otherwise, that's not true. We derived that and we took both of those into account. So that is, so they're just restating that a spontaneous change at constant temperature and pressure, the Gibbs energy decreases. And this picture is really, really what you want to think about. Something's not decreasing. What really is true is we defined Gibbs free energy in such a way that a minimum in the Gibbs free energy of the system is equal to a maximum total entropy of the universe. So really what you're still saying is the second law. If the Gibbs free energy decreases, it's spontaneous because the entropy of the universe is increasing if the Gibbs free energy is decreasing. So make sure that's really solid understanding of that concept. Nothing's really decreasing. We've just defined a function so that it decreases when the total entropy increases. There's another time that chemists find this new defined function really, really useful. And you've used it if you've done any electrochem in particular, because delta G you can show is equal to the maximum non-expansion work you can get out of a reaction. So let's look at why that is true. So we go back and start over and define the Gibbs free energy. And now we're going to talk about infinitesimally small changes, just because we may have to integrate at some point, but this will give us a more general equation. So once again, a change in TS, even if it's infinitesimally small, can change the S first and then the T, holding the other one constant. So if Gibbs free energy is H minus TS, then a change in Gibbs free energy is equal to a change in H minus a change in TS. And so it's minus SDT minus TDS. You can expand that. And now we can do some other expansions. So if the process is at constant temperature, which is what we have as one of our restrictions here, this is only true if the process takes place at constant temperature and pressure. So here we'll make the restriction of constant temperature, and we'll sub in how delta H changes or DH changes, because we know it's a function of U and PV. So H equals U plus PV. So DH will be DU plus PDV plus VDP. So all of this is the DH. We still have a TDS, but if we're carrying out the process at constant temperature, then this term goes away. And so we're down to DG at constant temperature is DU plus PDV plus VDP minus TDS. So if we want to think about this maximum part, the work will be maximum if the process is carried out reversibly. So let's think about what that means. So if we plug in, this is DU. du is how much heat's transferred and the work that's done. And each of, whoops, goes all the way over here, sorry. So the work would be expansion work plus any non-expansion work. So this is Q plus W. And if we have some expansion work and other work, we want to show that all these terms are going to cancel. So this will be our du. And now we have plus PDV plus VDP minus TDS. So if the process is reversible, which is what will give us maximum work, then we know ds equals dq reversible over t. So that means dq reversible equals TDS. So you can put TDS in here, and the second you do that, you're putting the restriction on that you're carrying out the process reversibly, therefore you're going to get maximum work. So as soon as you put in TDS for dq reversible, then the other thing you can do is you can see that negative PDV and plus PDV cancel. So we're then left with VDP, and now this TDS is going to cancel with this TDS. Put on our very last restriction, we're carrying out the process, the reaction at constant pressure, then this term goes to 0, and you've just proven that a Gibbs free energy change, if the process is carried out at constant temperature and pressure, is equal to the maximum amount of non-expansion work. So that would be work of electricity. So if you have electrochem, you'll remember that. Or the work of building molecules within a biochemical system. So any work that's not expansion compression work. And so, oops, stop and do this. No, don't stop and do that because that is already worked out. Sorry, that doesn't have a self-test after it. So, but do, so we've just gone through all of this. This is the derivation showing you why a Gibbs free energy change is equal to the maximum non-expansion work at constant temperature and pressure. But now go ahead and do self-test 3D.3 and then come back. And the last thing I want to say is, that's really, we've defined a new function, the Gibbs free energy, which is often done in science. We've defined it in such a way that it's convenient and useful because chemists often carry out reactions in open beakers where it's open to a constant pressure and the temperature is allowed to stay constant because you're not insulating the container. So under those conditions, we now have a function that will tell us, number one, is a process spontaneous? And number two, what kind of work, what kind of electrical or non-expansion work is available from the reaction that you're talking about. So if you understand, or if you can calculate the value of delta G for a reaction and the process is at constant temperature and pressure, you can decide if the reaction will go spontaneously forward or backwards. And you can decide how much non-expansion work you can get out of it. And that is the end of our discussion of just entropy in general. Now we're going to apply these ideas to understanding phase transitions and then to understanding chemical reactions.